Great, this is 2016 Physics 1. So another explain an experiment type thing. All right, so long track inclined at theta has some speed bumps. The bumps are evenly spaced, a distance d apart. The track is usually much longer than shown, with over 100 bumps. A cart of mass m is released from rest. Student notices after reaching the 40th bump, the average speed no longer increases, reaching a maximum value of the average. This means the time interval taken to move from one bump becomes consistent. Consider then from 41 to 44. So we know that it's consistent there. In the figure below, sketch the graph of the velocity from the moment it reaches. Okay, so if it's consistent, it's just going to be that. Yeah, and there's V average. Okay. All right, sketch a graph. Good. Over the same draw a dashed horizontal line at V equals V what? Okay. Oh, so I labeled it. So in other words, I did what they wanted me to do there before I actually had to do it. Great. Okay, cool. Suppose the distance between the bumps is increased, but everything else stays the same. Well, apparently, I mean, what they're saying is that this car has reached some sort of terminal velocity after a long time. So this velocity is really not going to change. So suppose the distance is increased. Is their maximum speed now greater than, less than, or the same as it was at the bumps closer together? Okay. Why would nothing will change because it's still at a constant speed? It doesn't matter how much distance is between the bumps when we're talking about speed, right? The same as it still reaches the same terminal velocity. So the max speed is still the same. I'm guessing that's what they want. This question seems really silly. All right, with the bumps returned to the original space and attack is trilled. Okay, so in other words, it's going to have a larger acceleration. It's going to reach a higher maximum speed. It'll probably still reach terminal speed, but there you go. Is it less? It's greater than, because the acceleration is proportional to sine of theta. As theta increases, A increases. We can also say the component of FG down track parallel increases, right? Okay, great. Oh, there's more, okay. Before deriving an expression for the quantity such as V average, it can be useful to come up with an equation that's intuitively expected to be true. No, not really. That way, the derivation can be checked later to see if it makes sense physically. A student comes up with the following equation, which is, okay, great. To test the equation, the student rolls the cart down the track with the speed bumps many times. Okay, the student varies the mass for each trial, but keeps everything else the same. The student graphs this. Is the data consistent with the student's expectation? Well, they're getting a constant slope, right? So there's a constant slope here, right? And so slope here would be delta V over delta M. And so if we look at this equation, so delta V over delta M would be CG sine theta over D, right? So yeah, absolutely it's consistent because CG sine theta over D is a constant. So we would expect that constant. Another student suggests that whether or not the data above are consistent with the equation could be incorrect for other reasons. Does the equation make physical sense? What? Well, I mean, let's just think about units once again, okay? Well, we actually don't know because we don't know the units of what C is. Does the equation make physical sense? I mean, let's see. We'll just say yes, because as theta increases, the average should increase, right? as mass increases, achieves higher v-tur, the spacing between, does the spacing between the thing so should the spacing, I see what the problem is. No, the spacing between the bumps doesn't affect the speed, the terminal velocity. The d is just like a way of measuring things. It's not actually a causative thing in the equation. Okay, and that is that silly problem.